All right, it looks like everybody's here. So before we start, I wanted to talk really quick about this week's exam and the final. Exam 4, I anticipate on having open and available to y'all tomorrow evening. It'll be roughly 7 o'clock when it opens up, and it will be open to y'all until sometime Monday. I'm thinking Monday at midnight is when I'm going to have it closed. It's going to cover everything from 5.4 up to 6.4. The final will cover everything except Chapter 6 material. The final is next week. It will be available to y'all all week, as will I. Except for a short period of time where I have a final myself, I'll be available to y'all all of next week to ask whatever questions you might have. The final will be about 3.5 hours long, so twice as long as a traditional exam. With that having been said, the final will be about twice as long in the number of questions as a normal exam. So I expect not more than 25 questions. Also, to that end, the final, it's going to be pretty much like our other exams. And in that way, I highly suggest everybody check out those study guides. Obviously, they're not for credit, but they are a pretty good indication of what the final is going to look like. You will find at least one question from every section in your final. Just like you would with a normal exam, right? Like, I don't know if y'all have noticed, but in the other exams, they usually pick something from the review section to be on the actual exam. So obviously, you're not going to be able to go through the entire reviews, all the study guides. There's like 60 plus problems for every section. There's no way to go through all of that. So what I would suggest is when you sit down to study for the final, go through all the study guides, identify the problems you know right away. Then say, all right, put those to the side. Let's tackle the problems that give us the hardest time. Focus all of our energy on solving those and understanding those so that when it comes time to sit down and do the final, they take less time. It's not like they're going to be done that fast, but they'll take less time, less energy, and it'll be easier for you to get through it. Also, to that end, when it comes to doing the final, I would suggest taking the same tack, attacking all of the problems you recognize right away, and then moving on to the harder problems and continuously getting more and more difficult as you do, right? So tackle all the easy problems first, then all the problems, then all the hard problems, and then all the what the fuck problems. I didn't say that, I'll bleep it out later. So with that in mind, having said all this, let's get on with today's lecture. Today's lecture is all over 6.4. 6.4 is about this idea of what's called an improper integral. So you have two types of improper integrals. Improper integrals that happen over discontinuities, and then improper integrals that are integrated from infinities or to infinities. So what do I mean? Well, what I mean is type 1 would be examples like this. Let's say we've got a bell curve. We want all the area negative infinity to infinity. This is the function f of x is equal to e negative x squared integrated from negative infinity to infinity. This is an example of the first type of improper integral. We're integrating from negative infinity to infinity. Having said that, notice we can break this up into two other improper integrals. Forgot the dx. All three of these integrals are improper. And they're improper because they have an infinity in the bounds. Now, as an example of another type of improper integral, let's consider the equation 1 over x. Now there are three different ways to have improper integrals here. There is, I'm going to break this up into two different areas. So there is the improper integral, negative 2 to 0, 1 over x dx. Then there's the improper integral 0 to 1, 1 over x dx. And then there's one other type of improper integral, negative 2 to 1, 1 over x dx. Notice this one breaks into two different parts, right? And what they all have in common is that they include the discontinuity of 1 over x. Make sense? So this section is all about how to handle these cases. And really, the method to handling them is pretty much going to be the same. The method is going to be rewriting. The method here is going to be all about pulling back and rewriting our improper integrals in terms of limits. So two examples of that first type. Again, integrating from negative infinity to infinity. And here we're integrating from 0 to infinity. So in the first type, the way we would handle this, and there are three cases here, right? 1, 2, 3. The way we would handle this is by breaking these up into limits. So in the case of negative infinity to infinity of a function f of x dx, we would rewrite this as the limit as c approaches infinity of the integral from negative c to c of f of x dx. In the second case, we have negative infinity to a value a, f of x dx. We rewrite this as the limit as c goes to infinity of the integral negative c to a f of x dx. And finally, the third case, the limit or the integral from a to infinity of f of x dx is equal to the limit as c goes to infinity of the integral a to c f of x dx. So we have all three of these cases, right? Notice too, again, this is equivalent to adding these two cases together, right? Also notice, I keep using c, but when c is our lower bound and it's going to negative infinity, I write negative c. This is a little bit different from what the book does. The book uses a going to negative infinity. They're equivalent statements though, right? Because if c goes to infinity, and our lower bound is negative c, then we're going to negative infinity, right? Okay, so how are we going to use all of this? What are we going to do here? Actually, before I go any further, there are two terms we really quickly need to touch on. The idea of converging and diverging. If something mathematically converges, it just means you get a number. You get an element, a value. If it diverges, it's the opposite case. So converging means you're going to get something other than infinity, negative infinity, or does not exist. Diverging means you're going to get infinity, negative infinity, or does not exist. Make sense? So, in this first example, we've got the integral from 1 to infinity of 1 over x dx. Now to solve this thing, the first thing we're going to do is rewrite it using a limit. We've got the limit as c goes to infinity of the integral 1 to c, 1 over x dx. So solving this is the limit as c goes to infinity of the ln of x from 1 to c this thing is now the limit as c goes to infinity of the ln of c minus the ln of 1. Remember, the ln of 1 is 0. Or we could rewrite this as, well, using properties of logarithms. The difference between two natural logs is the log of your first divided by b, right? So using either of these, we can reduce this case, or this solution, down to just the limit. I should call it an expression. We can reduce this expression down to the limit as c goes to infinity of the ln of c. But this thing's just infinity, isn't it? The ln of infinity is infinity. So, infinity. And we would say that this integral diverges. Everybody cool with this? So this first example is an example of an integral that diverges. Checking out now, the way the book goes about it, we have the integral from 1 to infinity of 1 over x dx. We rewrite it in terms of a limit. We evaluate the antiderivative. Then we apply our bounds. Then we do the arithmetic and apply the limit to get to our solution of infinity. So this particular example diverges because it doesn't give us a finite value, right? Now this example, I'm going to go ahead and tell you converges. But to actually evaluate all of this, we've got the integral. Folks at home, y'all can see that bar over on the board, right? No, you cannot. How about now? Yeah, you can see that. Cool. So in the second integral, we've got the integration from negative infinity to 0 of 1 minus 2x to the negative 3 over 2 dx. So rewriting this, this is the limit as c goes to infinity of the integration from negative c to 0 of 1 minus 2x raised to the negative 3 over 2 dx. Okay, now the question here is how do we handle doing this integration and keeping everything the same, right? One way to go about this is to apply u sub and rewrite your integration in terms of u substitution. So using u is equal to 1 minus 2x, we would plug in our lower bound to be, let me write this out this way. U sub u is equal to 1 minus 2x. du then is equal to negative 2 dx. Rewrite this as the limit as c goes to infinity of 0, my mistake, not 0. This is saying x is 0, right? So we'd have to rewrite this in terms of what u would be when x is 0. So it would be 1, 2, 1 minus 2 times negative c, so it'd be just plus c. This is one way of going about it. This is not the way I would suggest y'all do it. What I would suggest y'all do is hold off on the bounds, place them outside of everything. Do the integration just like you normally would. So I would suggest doing the integration, subbing our u back in after we do the integration, and then apply the balance. Does that make sense what I mean? Folks at home, do you follow that?
Yeah.
Yeah, awesome. So once we do all of this, we're going to have the limit, c goes to infinity, of u to the power rule here, right? My mistake, I meant to write -1/2. Power rule here is going to say add 1 up to the power up top, right? And multiply by the inverse of that power. Agreed? Let me just jump to the answer because I'm not going to do that in my head. After we apply u sub, we have the limit as c goes to infinity of 1 minus 2x from negative c to 0. Everybody cool with this? So now, plugging in our bound and leaving our limit as it is, we have the limit as c goes to infinity. Plugging in 0 here, we're going to get just 1. Plugging in negative c here, you're going to get 1 plus 2c. My mistake, I forgot the -1/2 power. This is going to be a rough morning for me. 1 plus 2c to -1/2. So we're sending c to infinity. This is a fraction here, right? So we have infinity in the denominator, so that fraction is going to go to 0. We're going to be left with just 1. Make sense? That is exactly what they're saying here. That after you go through, you apply the antiderivative, put everything back in terms of x, expand it all out with your bounds, right? And we're going to have 1 minus 1 over the square root of 1 minus 2a, because they're using a, not c here. When a goes to negative infinity, this thing goes to 0, and all we're left with is 1 minus 0, we're just 1. Now, I want you all to consider for a second what this actually means. Because it's actually it's both amazing and counterintuitive at the same time. Our function looks something like this. Right? You'll see that at home. Yeah. Okay. So what we've got here is this shape that looks kind of like this. And this thing has an infinite length. So it has an infinite length, but the area is equal to 1. It seems a bit counterintuitive, doesn't it? Because we understand that area can be thought of in some ways as a length times a height, right? Or an average height. So we have something that is infinitely long with a finite area. That is insane when you consider what that actually means, right? Personally, I think this is kind of a cool quirk of math, that things can be infinitely long and have finite area. That means the perimeter of the thing is infinity. That's insane. This actually shows up a lot in math. So as another example though, now we have the case of integrating 2x e to the x squared from 0 to infinity, 2x e to the negative x squared dx. This thing's going to be equal to the limit as c goes to infinity of 0 to c, 2x e to the negative x squared dx. So just another note about that last example. That also means that the integral converges. I should have pointed that out. But anyhow, so from here, once we apply u sub, we'd have e to the negative u du, right? So our answer should come out to be the limit c goes to infinity of this would be negative e to the x squared, negative x squared, from 0 to c, right? Everybody agree with this? So now we're going to expand it out. The limit as c goes to infinity of plugging in c first. We have negative e to the negative c squared. Just a note, this negative in the exponent is actually outside, right? We're not squaring the negative, we're just squaring the c. Minus 0 squared is 0. E to the negative 0 is still 1. So minus negative 1. Everybody agree? Okay, so from this point, I would rewrite this a little bit before we did anything else, just so we don't make any mistakes. The first thing I would do is rearrange our terms so that 1 is out front, because we're subtracting a negative, minus e to the negative something is like 1 over e to that something, right? So it's e c squared in a denominator. Like this, right? Well, if c goes to infinity, that means our entire denominator goes to infinity. So our fraction goes to 0, right? This thing just goes to 1. And again, we have another converging integral. This one goes to 1. So the area underneath this object of infinite length is just 1. That is insane. Again, it really does seem counterintuitive. So now, for the other type of improper integral, this other improper integral breaks up into really two different types. Okay. So here we've got the function f of x is equal to 1 over x. This area, we've already said, was the integral from 0 to, in this case, 1 over x dx. And this area is the integral from -2 to 0 of 1 over x dx. And then the area combined is the integral from -2 to 0 to 1 of 1 over x dx. Now, first thing I want to point out, we can break this integral up into two different parts. The integral from -2 to 0 of 1 over x dx plus the integral from 0 to 1 of 1 over x dx. Now the question here is, how the hell do we handle these? What do we do? Well, notice this is discontinuous, right? Our function is discontinuous at x equal to 0. And we only really care about what happens to the left of that, right? So we know we're going to need a limit, because that's what we've been talking about. And we know we only care about what happens to the right of that limit. So we need the limit from the right as c approaches our value from the right is going to be from c. Let me change this a little bit. I'm going to use t approaching c from the right up to b of 1 over, or of our function f of x dx is equal to t to b f of x dx. Okay, makes sense what I mean? Folks at home, does this jive with y'all? What we're doing is we're integrating from t to b our function f of x dx. We're saying that we want to apply the limit as t approaches c. We're saying that that thing is equivalent to the integral from c to b of our function dx. Is everybody cool with this?
Yeah, that makes sense.
Awesome. All right. So that would be this case here that we just talked about, right? That is this first integral down here. Now, we want to look at this second case. Here, we're going to apply the limit as t approaches c from the left. A to c of x dx is equal to, my mistake, t is equal to a to c f of x dx. So now we're really just flipping it, right? And then in the case where we have a discontinuity in between, so in this case, we would just break it up into these two, other integrals. Is everybody cool with this? Folks at home, does this make sense?
Yeah, it does.
Awesome. So we again would say that these integrals are convergent if they give a number. But if they give infinity, negative infinity, or does not exist, then we would say that these integrals are divergent. So, looking at our first example, we've got the integral from 1 to 2 of x minus 1 to the negative 1/3 dx. Notice here, when x is equal to 1, we have a 0 in the denominator. So we have a discontinuity at 0, right? I mean at 1. So we need to rewrite this thing in terms of limits. It would say that as the limit of t approaches approaches 1 from the right, we're integrating from t to 2 of x minus 1 to negative 1/3 dx. This thing would come out to be the limit as t approaches 1 from the right of 3/2 times x minus 1 to the 2/3 power integrated from, evaluated from t to 2. So now, we expand all of this out. The limit as t approaches 1 from the right of, throwing in 2, we're going to get 1 raised to the 2/3 power, which is still 1, times 3/2. So this first term is just going to be 3/2 minus 3/2 t minus 1 raised to the 2/3 power. Well, in the limit, as t approaches 1, this thing goes to 0, right? So we're just going to be left with 3/2. So our answer here is just 3/2. Everybody cool with this? So here what we've got, something else that's cool. So first, this integral converges, right? Because it gives you a finite value. But something else that's cool is that here we've got a function that is infinitely high with a finite area. So again, another shape with an infinite perimeter, but a finite area. So just because the perimeter of a thing is infinity doesn't necessarily mean the area of that thing will be infinity, right? Which again is totally counterintuitive. We're used to thinking of yards fenced in, the larger the perimeter, the larger the area, but that's not necessarily the case. The two don't totally bound each other. So looking at, well, yeah, that's all I wanted to say about that. Looking at another example, you've got the integral from 1 to 2 of 2 over x squared minus 2x. Now here, they use what's called partial fraction decomposition. For those who are not familiar with it, I added a section at the very end of these slides about it, just so that if you needed to, you can quickly review it. But the idea of partial fraction decomposition is just that it gives you a way of expanding out a fraction so that you can integrate it more easily. So look at what this all does. We've got 2 over x squared minus 2x. Now our first intuition might be to expand this out, or to factor this out, to be 2 over x times x minus 2 dx. Okay, so we see we have a discontinuity at 2. So we know from this, we need the limit as t approaches 2. This time, we're coming from the left of the integral 1 to t, 2 over x minus 2 dx. Now, what partial fraction decomposition does, just very quickly explaining it to y'all, it lets us break this up into 2 different fractions that are easy to integrate. Because notice here, there's no easy trick to integrating this, right? Like this could be by parts, this could be u sub, there's a bunch of different methods we could apply here. But if we use partial fractions, we can break it up as the limit t goes to 2 from the left of 1 to 2 of, this comes out to be 1 over x minus 2 minus 1 over x dx. And from here, we do everything just like we normally would. Everybody cool with this? So like I said, for those who aren't familiar, from here to here, we use partial fractions. And you can find those at the very end of this section, or of these notes. I put an extra section in there just to review this idea. Because it's a really good trick, right? Like, who wants to integrate that when you can integrate that? You know what I mean? Okay. So another example, we've got x to the negative 3rd power integrated from -1 to 2. Now notice x to the negative 3rd has a discontinuity when x is equal to 0, right? So what we're integrating is this picture right here, or what we're finding rather, is this picture right here. The integral from -1 to 2. We have this discontinuity at 0. So we have to break our integration up into 2 different parts now. Here, we've got the integral from -1 to 2, x to the -3 dx. This thing is equal to 1 to 0, x to the -3 dx, plus 0 to 2, x to the -3 dx. But x to the -3 is discontinuous at x equal to 0. So we're going to apply our limits to these 2 integrands, right? Here, I rewrite it as the limit as t approaches 0 from the left of the integral from -1 to t x to the -3 dx plus the limit as t approaches 0 from the right, the integral from t to 2 x to the -3 dx. We handle this just like we would any other integration. Is everybody cool? And that's what their point is here in the notes. Is that once you identify the fact that you have a discontinuity at 0, that 0 sits in between your bounds, then you know to break up your integral into those 2 parts, and then to rewrite it in terms of those limits, do everything like we've been doing. Cool. So having said that, there really wasn't much more I had to say about all of this. One of the applications to these problems or to this idea is the probability theory. Under the bell curve, we have an area of 1. So by integrating between different bounds, you get the probability of an event happening. And it's all because the integration from -infinity to infinity is 1. So it's a really cool tool in that way. And that was really all I had to say about all of that, other than to make a note about this present value of perpetuity. Present value of perpetuity assumes that C of t function we had in the present value, that it's going to be constant now. We're just assuming that this is like an annuity. You're paying the same value over time. It shows a constant. So then calculating present value forever turns into calculating from 0 to C or to t1 equal to infinity, right? Where that C of t is now just a constant p, e to the -RT dt. When you evaluate this integrand, it comes out to be p over r. That was the only other thing I really wanted to touch on here. And there is a proof for that if you wanted to look at it. Having said that, that is all I've got for y'all. I'm pretty sure it is time to go. It is one after. I'll stick around if y'all have any questions.